Dear colleagues, I'm Mikhail Tsventoukh from Lebedev Physical Institute. I will talk about plasma physics. There's intense plasma splashes from a sun that provides many solar flares, and there is a year of enhanced solar activity, and maybe you also have saw aurora borealis, because it spread over all Earth almost until the equatorial plane, and you can see here not the borealis shining near equatorial plane at some very softened part of the world. So you can see here plasma flares pressed away from the sun, and here modeling of few days arriving of plasma from sun to the Earth, then it hits the Earth. What happens here? Magnetic field of the Earth, as most of magnetic fields in universe, has a dipole form, and particle can move freely along the field lines and not so free across field. So particles can reach Earth's surface at the poles, north and south poles. And so it's called aurora borealis because of magnetic field structure. But what makes plasma of large intensity? Let's consider, for a lot of plasma, let's consider magnetic hydrodynamic equations. There is continuity equation, there is Newton's law for a droplet, or for a droplet of plasma. In fact, there is a hydro part is a minus gradient of pressure, and there is a magnetic part is ampere force. And if we combine this equation with the Maxwell equation, we can get that magnetic pressure acts on plasma as a plasma pressure, and it pressures plasma outwards of the plasma pressure together with magnetic pressure. So it acts similarly to plasma pressure. Additionally, if we use Faraday law, another Maxwell equation, and Ohm's law, we can get for very large conductivity of plasma, we can get that the electric field should be minus V cross B, and we can get the equation of evolution of magnetic field. This equation means literally that magnetic flux is conserved. So B times some transverse area is conserved. So solar plasma can compress the magnetosphere, can compress the magnetic field, and it heats the magnetosphere and compresses it in size. So there is a reduction of size and increasing of magnetic field. This equation describes frozen in of magnetic field lines into the plasma. So they move together, and there is conservation of a magnetic flux. And then plasma arrives with its own magnetic field, or no magnetic field, and hits the magnetosphere. Magnetic field will be enhanced, and this is called magnetic storm. Also, one can see spiral sleeve structure of the magnetic field from the sun that extends together with plasma. So not the magnetic field and not the plasma move freely, but magnetic field is frozen into the plasma. A counter-directed magnetic field can annihilate, and this annihilation gives acceleration of particles. It calls magnetic reconnection. It is intuitively clear that plasma should be expanded away from a large pressure. And we have saw before that it should be pressed away by the magnetic pressure as well. But conservation of magnetic flux gives us ability to consider some configuration of stable plasma confinement. Let's see, this equation is adiabatic equation of state that is in fact thermodynamics. this pressure, volume, and adiabatic exponent is a constant. We have used this equation together with conservation of flux. So we can derive that specific magnetic volume, which is the integration dl over b, should be constant to get a stable configuration. So there is namely there is large volume and low pressure, and large pressure and low volume. And frozen in magnetic field lines means conservation of magnetic flux, give us ability to get a configuration with stable confinement. So there's no convection in this configuration, but stable pressure gradient in accordance with the magnetic configuration, which also has a gradient of a specific magnetic volume, which is integration del over b. But why we have omitted collisions and treat a plasma as a superconductor? We can do this, in fact, if collisions are very rare. Let's consider electron momentum conservation equation, which is written here. And for stationary conditions, there's no acceleration. Electric field is compensated by retarding force, which is written here. So there is some drift, constant drift motion along the distance. Current density can be deduced from this equation, and it depends on the relaxation time. The collision frequency, or inverse relaxation time, can be estimated as concentration times velocity times sigma, which is the cross-section of an interaction. In fact, it is an area of a target that they have to hit. But the collisions in a plasmas are different from a collision in a gas, for example. Collisions in a gas mostly like hard spheres. So you can see here, experimental movie. Plasma consists of charged particles, and they interact by Coulomb law. So there is smooth deflection of charged particles from one to another. One may estimate energy of Coulomb interaction as E square of the radius of interaction. This gives us to deduce a cross-section of Coulomb interaction, which is inversely proportional to the energy. So the larger energy, the lower the area of the interaction. So in fact, we can get very low interaction or almost no interaction if we have a hot plasma of high energy. Let's integrate this value all particles in a plasma. But there's a problem arises as we have to use all of particles. So too much, we cannot perform this integration because Coulomb potential vanishes at infinity. But we have to consider here finite number of particles. We can get so-called screened Coulomb potential at a distance which is called Debye length. We can get simple estimation of this value from a Poisson equation, and for given temperature of electrons and given concentration of electrons, we can get this value of Debye length. So the potential is not more Coulomb potential, but in plasma we can screened potential, which reduces exponentially with a specific length, which is Debye length. You can see here. So strictly speaking, we should consider as a plasma an ensemble of charged particles of size larger than Debye length, of course. And we can use this Debye length into integration, and it gives us some restriction of number of particles that can be involved in interaction. And we can get this perform this integration, and we will get so-called Coulomb logarithm. This value reflects all of particles, contribute into the interaction and contribute into the cross-section of Coulomb interaction. In fact, for most of plasmas, it ranges from 1 to 20, and typically it can be considered as 10. So 10 times larger than our simplest estimation that we drew in the previous slide. It's worth noting that most contribution is from smooth angle scattering. On contrary to the hard spheres, it is intuitively clear that hard scattering gives most of contribution. In plasma, on contrary, due to Coulomb interaction, we can find that a large number of particles with small angle scattering contribute mostly into the scattering of plasma and into the collisions in plasmas. Another important feature of plasma is Langmuir plasma frequency. It is the frequency of oscillation of electrons that provide this screening at the byte length. So we can use the byte length and estimation of velocity of electrons, and we can get this plasma frequency. There is critical density of plasma electrons, which corresponds to a resonance between plasma electrons oscillations and external wave frequency. The efficient absorption of energy from laser or from electromagnetic wave, then this resonance occurs. In particular, for optic wavelength, one can see that density is about 10 to 21 per cubic centimeter. This is more than tenfold larger than atmospheric pressure gas density and substantially lower than solid state density. So for effective absorption, one needs to use some porous material. It was done recently by using of carbon nanotubes. It was a nest of carbon nanotubes that was irradiated by intense laser in femtosecond range of duration and of large intensity. And it was found that very good conversion from energy of laser into the hard X-rays. You can see here the reference on modern articles from previous year. Plasma oscillations can be used if there is no efficient collision mechanism for producing resistance of plasma. It was old work, maybe one of first work with the numerical simulation of plasmas by a computer was done by Oskar Bunnemann in 1959. He has discovered two-stream instability of plasmas. Instead of collisions, one can use scattering by plasma oscillations. This can be helpful for slowing down of so-called runaway electrons. For large energy, there is low scattering by Coulomb potential, and electrons can be accelerated very intensely. But plasma oscillation does not depend on energy, and they can scatter these accelerated runaway electrons. Not so old modeling, almost recent modeling, has been performed of strong electron turbulence that can drive the rise of the potential plasma and transfer the energy of a directed electron beam into the temperature of plasma. You can see here the plot with the phase portrait of the electrons. Some of them move forward, some are reflected backward, and you can see strong growth in the potential. This large temperature, and this temperature forms this large potential. This holds obviously up to heavy component acceleration, namely ions. Then they are accelerated and pushed away towards plasma disappear, and acceleration mechanism is disappear. But an important point is this modeling demonstrate exceeding of the plasma potential of the applied potential between cathode and anode. It looks strange. It can be illustrated by a simple model of floating potential. If you embed isolated body into the plasma or immerse plasma into some chamber, the wall be of a so-called floating potential. This floating potential can be deduced from equality of two fluxes of ions and electrons, written here. And it approximately is about 3 to 5 electron temperatures. For the metal plasma from previous slide, it is about 5 temperatures. So strong electron beam emitted from cathode is accelerated to 5 electron temperature and drives this directed motion into the new temperature. So it's positive feedback between acceleration and potential growth. As it obvious, it occurs until the heavy component, the ion acceleration, away from plasma. So it is transient event, of course. Returning back to the magnetosphere, one can see that field lines near the poles has a conical shape, and a particle can reach the atmosphere of Earth, then it falls into the cone. It is known from mechanics then particles have finite motion. There is adiabatic invariance at nearly the constant. Here we have a finite motion, rotation of the particle in the field, and there is adiabatic invariant square of transverse velocity over the B magnetic field. It is conservation of flux of the single particle. To get inside the cone, one should have longitudinal velocity larger than transverse velocity, and boundary is given by the loss cone angle, which is written here. It depends on the amplitude of the magnetic field at starting point, minimal field, and at large field, then there the magnetic field makes a bottleneck. It resembles a reflection of a particle from bottleneck, and one can use it for confinement particles. If you create two bottlenecks, you can have a trap with a confinement particle with reflection from two mirrors from two bottlenecks. It was proposed in early 50s by Bootker and Post, and calls mirror device, or propkatron in Russian. It seems that confinement should be good because the solid angle of the bottleneck is small. It's hard to get inside this cone. But we have a plasma. As we have saw before, we have scattering into small angles. So smooth scattering provides very fast losses from the bottlenecks. So plasma being pushed away from bottlenecks very efficiently. So what we have to do? We can use chains of bottlenecks, chains of mirror devices, or we can combine them into the torus. So we can get closed corrugated traps. Another adiabatic invariant, namely a longitudinal adiabatic invariant, which is integration over the longitudinal velocity between two mirrors. And it helps to examine the drifts of charged particles in a non-uniform field. In particular, one can say that drift velocity, which is average motion in a non-uniform field, is a gradient of the second adiabatic invariant, longitudinal adiabatic invariant. Particle drifts in non-uniform field is directed transversely both to the B field and the gradient of the field magnitude. One can see if there is a gradient of magnetic field amplitude with different Larmor radius of particles. The larger field give lower radius of duration, and the lower field give larger radius of duration. So there is a drift as an average motion, and it depends on the particle charge. So electrons and ions move in opposite directions. This means electric field arises, and this field can drive whole plasma towards E cross B direction, namely into the weak field. Recall that we have saw that plasma is pressed away by the pressure and pressure of the magnetic field. So the large pressures away plasma in MHD description, in magnetic hydrodynamic description, and here they can solve the same thing from the kinetics of charged particles of plasma. So we can use the distribution of longitudinal adiabatic invariant to study an optimization of the magnetic configuration from point of view of particles drifts. This rather complicated system, but it is still a stellarator Wendelstein-Zebenix. It started to operate in 2016 in Greifswald in Germany. As in fact, it consists of two linked mirror devices. As you can see here, is 5-period linked mirror. This device, before the construction, was optimized from point of view of plasma particle kinetics. They drifts in non-uniform field, which is given by longitudinal adiabatic invariant. The longitudinal adiabatic invariant can be used instead of specific volume of the magnetic flux tube for stability examination. It also reflects some area, some volume, which is available for a particle motion. It could be used for the stability analysis. Kinetics is more appropriate for hot plasma than MHD, than magnetic hydrodynamics, and it gives both necessary and sufficient stability condition. There's the MHD gives only a sufficient condition. So it means that the critical pressure gradient in a given magnetic configuration can be somewhat larger in a kinetic description than in simple MHD description. We can use it for a linked mirror device, consists of several mirrors, and find that there can be very large discrepancy between these models, and the necessary and sufficient condition give very steep pressure profiles instead of the MHD, which predict just zero gradients. Why we have to confine the hot plasma? We can get the energy from it. All of our energy is in fact nuclear one. It can be extracted in an Einstein equation, or most known Einstein equation, during the fission of heavy elements or fusion of light elements. The energy is very large. As it known, it is about a few mega electronvolts per nucleon. Sun uses fusion for providing energy, but it is have large size and large time. If you want to realize fusion in a Earth condition, we have to use much more intense reactions. So you can see here the cross sections of nuclear fusion reactions of hydrogen isotopes, and specific energy for this process is about 10 kilo electron volts. 1 electron volt is about 11,000 of kelvins. So the temperature of the media of plasma should be about hundreds of millions of kelvins for achievement of fusion of light elements. That's why we have to use magnetic field, because typical matter cannot confine such a media. Most advanced device for plasma confinement is a tokamak device, which has two components of field. One field is longitudinal field, or toroidal field, is produced by a toroidal solenoid, and other component of field is produced by a current flowing through the plasma itself. So resulting magnetic field has a spiral shape. It should be elongated in longitudinal direction to the plasma stability. You can see here the geometry and some results of modeling of plasma turbulence into this elongated helical structure. One of recent achievement in plasma physics, in tokamak physics, was a negative triangularity. It was very positive, surprisingly, for the plasma confinement and for plasma performance. It was very well known that it is good to use vertically elongated torus, and it allows to get good regimes and good plasma confinement. It was known for decades. And recently, people use inversely shaped configuration when plasma is convex to inward, not the outward. It allows to substantially improve plasma performance and to reduce plasma surface interaction. But there is a lot of fundamental studies in plasma physics and interesting new results. Thank you very much for your attention.